Okay, hey again. So this is lecture two. Um, it's only the first week of school, and I am completely overwhelmed, quite frankly, dealing with all the classes, and none of my classes are the same. Um, if you email me and I respond with like one line, it's because I'm dealing with like 100 different emails. The labs are just a nightmare right now. We have this mix of the online and in-person stuff, as you know. We also have our first positive COVID case, so if that number keeps going up, who knows, maybe all this will move to online, but I'm sure they'll let us know as this goes. Um, as for the labs, I know I told you guys before that you could stop in the labs and come see me. I haven't posted my lab schedule, just 'cause I forgot, but real quickly, I'll post it in an announcement so you have it like kind of written down. But I teach Mondays from 10:30 in the morning till 1:30. Um, and then Thursdays I teach from 10:30 to 1:30. And then I also teach later at night from 7:30 until 10:30 at night. And then Saturdays the next day I teach, which is again 10:30 to 1:30. Um, So yeah, I mean, if you really want to stop by or you have any questions or whatever, I don't know the room numbers off the top of my head. I know that Monday 10:30 to 1:30, I'm in room 261. I think it's all the labs, but I am teaching three different labs, so they are in different places. But just to give you a general idea, I'll write it down in an announcement. But yeah, so this is going to be the second lecture I do, kind of in the format the same as the first one. I'm going to try to switch it up. This is not the most ideal way to do it. I know it's probably really difficult for you. It's really difficult for me to even try to do it this way. Um, but I have ordered a pen, like a digital pen, so I can actually write things as I'm talking about them, which I think would be more like a lecture. I've never done that before, and I don't own one, so it should be here in a couple days, and then I may try the next lecture like that, or I may just go to school and try to find a classroom that's not being used and just film myself in front of a whiteboard or something. So yeah, so if you don't like this method, I'm gonna try to improve it. It's definitely not easy on me. I'm kind of explaining things and talking to you, and you can't even see me, and yeah. But anyway, let me try to get rid of these windows. So I don't have a good way of recording this either, so I'm recording it on WebEx, like the Microsoft WebEx, like the sort of like Zoom thing, which is probably a dumb way of doing it, but whatever. Um, okay, so what is this chapter about? This chapter is like the first real chapter of physics we're actually doing. The first chapter was just kind of like a bunch of generalized science stuff you should have learned in high school, maybe even middle school. So we're moving on from there. So most of these word pages I'm going to skip. You can read that in your own time. Um, just defining kinematics for this chapter only. We are just doing. It's basically one-dimensional kinematics. So it's going to be like a lot of cars moving, guys walking to the left or right, or stuff moving left or right, just in a single straight line. Uh, it's talking about like particle-like objects here. So basically, it doesn't matter what you're talking about. It could be a car, a spaceship, a flying banana, whatever. We just consider them particles. It's just a dot. And as you get farther along, we'll continue doing this even when we get really complex objects, maybe that you're looking at in space. Basically, you just find the center of mass, and then you make it a point particle from that point, and it's much easier to deal with. So we're going to do the same thing here. Um, it's saying like like an electron, that kind of thing. But the truth is, something like an electron, we've never seen one. Nobody knows what an electron looks like, right? So we always have this image of like a little green sphere, right? That's what we say an electron is, but we really have no idea what it looks like. But it makes it easier to deal with. So one of the other things they're talking about here, and again, this is hard to explain without a whiteboard and to show you, but you're going to deal with coordinate systems. This is the most basic introduction to a coordinate system we're dealing with, and that's why we're starting in one dimension, right? So the coordinate system you are choosing. It is up to you as the person who is doing a problem, working out the math, whatever. You can choose whatever you want for a coordinate system. But the thing is, if you choose the wrong one, you're just going to make your life more difficult. And it doesn't matter, you should always get the correct answer if you know what you're doing. So the easiest way to put this is you always want to choose the easiest coordinate system. So for instance, we have this positive and this negative direction on this like x-axis, right? It's like a number line. So if I decided to spin the coordinate system like, 90 degrees or something, that makes everything a huge headache, right? You got to change like your x-axis to your y-axis, and then everything becomes confusing. Or even worse, you make it like 45 degrees, right? So then you got to start taking cosines and sines of everything. So basically always it's not going to make as much sense right now because again, this is just an introduction, but as we get further along in this and we do two-dimensional stuff, it'll make more sense. And it has more to do less extreme stuff like spinning a coordinate system around and more like choosing where your 0 point is. For instance, on this number line, if we say a guy's walking and he walks 3 meters, so that's from 0 to 3 on this line, you'd want to start him at the 0 mark, right? You wouldn't want to start him at like 3 and then he walks to 6. Like you can choose that because then you're just adding extra math. It's not saying you can't do it, right? It wouldn't be hard, but as these problems get more complex, it will become harder. So just choose the easiest one. Okay, so just some terms here. A change in position, which is that little triangle, it just means the change of. You should have learned this in some other math classes before. But there is and my cat is attacking something in the background, and so just ignore any random noises you hear, I guess. So the displacement is, like I said, the change of x. Some basic math stuff you probably learned way back when you first started some algebra, maybe in high school or whatever. You just have final position minus initial position, and that's determined just to not give you a negative answer, but it also depends on that where you picked that coordinate system, right? So it's again, it's a convenience that you choose. So if you don't want to deal with negatives, you choose the coordinate system in such a way that you don't end up with a negative. But again, it's up to you, but you have to be good enough to be able to interpret what the information you got is. Okay, so, and you're not going to be at that level yet. So keep things like it is now, x2 minus x1. That's what the change of x means, the little triangle x. This is a calculus-based course, right? So the thing is, this is a very introductory calculus-based course. If you ended up taking this with some of the other professors, they don't see it as the same, and they will teach it very differently. They will be very heavy on calculus. But as Calculus 1, I believe, it can be a co-rec for this class. So some of you may be taking it at the same time as this. You may not have learned everything there is to learn that we're going to go over in physics. I can warn you right now that most professors, if you go to ask them a question, especially in physics, they are only going to want to answer the question about physics. Math is a separate subject. They kind of look at it as, if I could make an analogy, it would be like English. So somewhere along the lines, you learn to form letters into words, and you put these letters together, and you can make lots of words. The physics professors want to look at the book you've written. They want to analyze the literature. They do not want to spell check and see if you know how to put a word together and is it spelled correctly, does it make sense, that type of thing, if that makes sense. So most people in physics don't want to check your math. And the problem is that most of you are going to have most of the problems in math. So try to keep that in mind. You can definitely look up a lot of math stuff online. Again, you can come to me if you're having problems with it. But as far as this being a calculus-based course, I keep it very introductory level. We try to introduce you to some calculus in this and where it's going, but it's more heavily based in algebra for this. So this change of x you see, the triangle x, or delta x, is going to eventually turn into dx, which is a calculus-based infinitesimal piece of x, right? So, but we're not going to worry about that right now. Just know that in the future, this is going to change to dx. Okay, so vectors. You guys are going to do vectors in the lab when you do the 180 lab. The vectors, remember, basically it has a magnitude and a direction. You need those two things. That's what defines a vector. So if I say that I am going 60 miles per hour, that is not a vector, right? That is what you call a magnitude. It's just the speed at which you are traveling. If I said I was going 60 miles per hour northwest, that gives you a direction. I've now given you a vector. You can see the direction and speed at which you're moving. That defines a vector. So what they're talking about down here at this part, ignoring the sign, absolute value, whatever, if we just took this as 4 meters of displacement of x, then that is the magnitude, right? You moved 4 meters. If I then assigned a negative and a plus, you can tell which direction it's going. So you get more information about where it's going. So hopefully that makes sense. Things like your typical variable x, which is going to be a distance or a location if it's just a single x point. That position is then just a magnitude, right? If you take something like a velocity is a vector, right? So you need the speed and direction it's moving in. So, and you'll define more of these. The lab's actually pretty helpful for this. It'll make more sense when it's in front of you too, and you can kind of play with things. The thing you'll do in the lab, it has the vector lines or strings and weights, and you can move them around and add and subtract vectors. If I had a board, I would show you how to add and subtract the vectors right now, but I don't have that available. If I remember in the videos, I may do a little something as a refresher course, but it should be something you've seen before. You should have done it in high school at some point. I understand a lot of people, maybe you're 10 years out of high school and you haven't seen this stuff in a long time, or you didn't pay attention or something like that, but you can definitely look it up, look at videos on YouTube or whatever. Okay, so, and I skipped the checkpoint thing, so there's the answers to this. I didn't even read it. Which pairs give a negative displacement? So, yeah, it's you can go over that on your own. It's sitting there. Okay, so they're talking about average velocities. An average velocity, is just something you can take if you have different velocities. This should be pretty, I don't know, this should be pretty obvious. You should know what this is. It's just, it's showing you that it's making that delta x and that delta t and pulling it apart and defining it as the x2 minus x1, which we saw in the previous slide. And now we're just adding another component of time. So you get like a final time minus an initial time. And generally, if you're dealing with the times, the time might start at 0 frequently because you can be in control of that a lot of times. But, and then, you divide a distance by a time, you're going to get a velocity. Okay, so graphs. If you don't like graphs, you're probably in trouble. Physicists love graphs. They love plotting things, slopes, all this stuff. It makes more sense to you the further you go. A lot of times you're going to ask yourself, why are we doing this? I don't know why I'm making a graph or whatever. So when you make these points on the graph, like there's 2 points on this graph, one here and one here, right? So by intersecting it with a line, we can draw a line. When you do this in the lab, you're basically averaging the data points, right? So you got a data point here, you got a data point here. If we had more data points, like maybe one up here, maybe one down here, then this blue line would follow more the trend of those data points that are giving us. But for now, basically you just want to be able to read a graph and get the information from it. So in this one, we want to see that basically we have the X, it's not X-axis per se, because it's, it's up and down. It's typically not what we use for the X-axis, but this is just saying X as in meters is in this direction, and then time is the normal X-axis over here. Well, when you do this in a lab, again, when you plot, you want to label your axes, and then you also want to label the units you're using. So this is time, we're measuring it in seconds. This is distance, we're measuring it in meters. So then this is just X as a function of time. So what else was this going over? So they're talking about the slopes and how you can get a negative and a positive average velocity. And there's some other pieces over here. If you don't remember how to get more information out of the graph, you can look at this. But it should be pretty straightforward. Okay, average speed, same distance. I think there's some better examples that will play this out instead of me just talking about it forever. Average speed is always positive. You're basically taking like absolute value bars outside of it, which means you're taking the magnitude of it. So this is a problem. I'll have to do this in a separate video, which I may not get up right away. I may post this video as the lecture first, and I may have to film the problems afterwards, because it's about 11 o'clock at night right now, and I have a lab first thing in the morning. And as soon as I get done that, I'll try to do the problems and get them posted. But just know it'll be a little delayed. And anytime I delay posting something, a video of a problem, a lecture, anything that might happen, I'll always give you extra time on homework or whatever. I'm not going to say like, hey, I was late getting this to you. By the way, it's due in an hour or something. I'll give you more time to do it. So don't worry about that. Okay, so learning objectives. Yeah, we did that. Okay, so here's where we get to converting some more of this stuff into your delta x and delta t at the bottom. You're taking a limit as it approaches 0, and you're getting this now calculus-based looking thing that you may or may not have seen before, where you're getting dx over dt. So for the purposes of right now, this basically means the same thing. The delta x, or change of x, is the same as the dx, right? The delta t, or change of t, however you want to say it, is the same as the dt. Speed, again, we've noted that is a magnitude. Okay, so yeah, here's a quick checkpoint thing. You can read this and do it on your own real quick. I don't think these are too hard. Click the next frame, then you get the answers, so you can check that. Okay, on to the graphs. So we're getting more into the graphs, more information from the graphs. Point of these, velocity of an elevator cab over time. And it's just giving you more information. So we can see time on the x-axis, and then you have the position again, which is in meters on the y-axis. So if we follow this, we can find different points in here. You can see from 3 seconds on the top graph to 8 seconds, it's a straight line. So we know how to deal with that in regular algebra fashion. Anything that has a curved line, you're going to need calculus to deal with. The bottom graph, which you can see is just straight lines, is then easier to deal with without calculus, right? Yeah, you can see the same thing. It's time. So this is a position versus time graph. This is a velocity versus time graph. And you need to be very careful with the axes and what they are showing you, because the graphs are not going to always be the same. Position versus time is not the same as velocity versus time, right? So don't get them confused. Here's another page you can go over on your own. So we have average acceleration again, and then you have an instantaneous acceleration, and you're looking at a single moment in time. So this is then just dv dt, and for right now, I'll have to look at the homework problems, but again, you're probably going to be mostly dealing with the top version where you're doing algebra-based stuff. If I can find one, because I haven't looked at the problems in this book, if I can find one that has calculus base, maybe I'll give you one just so you get an idea of what it's like, but I'm not even sure if they have them because I haven't looked at it, but we'll see. If you look at the equation 2.9, and I'm pointing it at with my finger and you can't see that, but so if you look at this equation, this right here is the way it's written. We are taking the velocity and you are taking a derivative of the velocity in respect to time. If you're looking at this, then we are taking the position derivative in respect to time. Now, this means that we're doing it a second time. We're doing this whole inside portion as a second derivative in respect to time, right? So that's what this is saying. This is saying this is the second derivative of x, and it's over dt, so it's in respect to time. And basically, you have to take the derivative 2 times. Okay. More of you're going to have a lot of stuff with positive and negative, and they've tried to lay it out in such a way that there are rules for positive and negative so that it makes sense. But here's the thing, the best piece of advice I can give you is if you're ever confused about a positive or a negative, just pick one, go with it, get to the end of the problem, and then say, does this make sense? That's going to be the easiest thing. You know, did you calculate something and it's taken -3 seconds or something? That's not going to make sense. Was it falling downward and, you know, it's... I don't even want to say it. So, because without drawing it, I don't think it's very easy to understand. But most of the time, you're going to be able to say, this doesn't make sense. I need to flip this negative sign. Okay, so checkpoint 3. It's talking about this wombat that moves along an x-axis. What is the sign of acceleration if it is moving in the positive direction? And then there's all these different examples. So this is talking now instead of about initially at a positive negative velocity, it's talking about a positive and a negative x-axis. Okay, so A, it's saying in the positive direction with increasing speed. So basically positive speed, so it's positive positive, so it's going to be positive. B is in the positive direction with decreasing, so that's basically positive negative, so that'll be negative. C is in the negative direction with increasing speed, so negative direction and then positive, so C overall will be negative. And then D in the negative direction with basically negative speed, so negative negative, so it's positive. So A should be positive, B and C are negative, and then D is positive. If that made any sense. Just, if it doesn't make sense, pause it there. There should be also some examples in the book. Maybe go over them and make sure you understand it. I promise the positive negative stuff gets easier. I know it's confusing right now. Okay, so we're back to graphical representations of acceleration. So we have some, what it's talking about here. You have to be careful again, because like this is velocity versus time. So if you have a position versus time and you have an increasing slope like this, it, like if you try to derive things like acceleration from them, they don't mean the same thing. So in a velocity versus time graph, this from here to here, the velocity is increasing, right? So there's an acceleration here. When we go from B, we can see it's 4 meters per second. Over to C, it's still 4 meters per second. So there's no acceleration here. It's moving at a constant velocity. So don't get things like constant velocity and constant acceleration messed up. Again, it's going to be a lot of information. Make sure you discern between the two and whether it's a velocity versus time or position versus time graph. When we go from C down to D, then it's a negative slope. right? So velocity is decreasing as you go, and it hits 0. So when it hits right here, basically we went from 4 meters per second to 0 meters per second in 1 second. And then it just stays at 0 for however much time continues according to the graph right here anyway. This one, so this is just basically explaining that where the acceleration is happening. So you can see as you have this upward trend here, we're accelerating. So it's saying basically if you transpose these points straight down, that we're going to make the acceleration more apparent down here. So it's the acceleration has gone to 2 meters per second squared right here, and then gone back to 0. Because like as we stated here, the velocity is not changing. Velocity is 4, velocity is 4. We go down here, follow the lines from here to here, acceleration 0. Then we can see it rapidly deaccelerates, right? And that's what this is saying. This is showing you that it deaccelerates right here, and then acceleration goes back to 0. Okay, here's another problem. We'll go over this later. More learning objectives. You can read those on your own. So again, here we go with these position versus time graphs and slope versus time graphs, or velocity versus time graphs. It just has the slope in there. So just be careful which one you're reading and how you read them. You're going to go over this in the lab too, so it's going to try to kind of screw with you there too. So just pay attention, read it, be careful. Okay, so here we're getting into the more important stuff. So these are the basic kinematic equations. You're going to use these for the rest of the semester, depending on your major, maybe for the rest of the time you have a career. I don't know. Could be a while, but these are very useful. So when you go through these, this is again something I need to do on a board, but you can kind of see it's kind of showing you where it comes from, how it's derived, and not in a great way. And then it has this equation 2-11. That equation that's in that beige box is super important, right? That's one of the basic kinematic equations. So I'm just going to move on from that without being able to do anything else. So basically they're going through and then deriving basically the second equation. And again, beige box and result. This is the super important thing you're going to use. It's good to know where this stuff came from, so you're just not using it randomly. But basically that equation at the bottom is another huge equation that you're going to use all the time. Remember that the, again, down here, x minus x, what they call x naught. They'll call it naught a lot. And that just means 0. And you can say x minus x0 if you want, but sometimes it's confusing because you have actual zeros in the problem. So a lot of times we say x naught. X naught just means initial conditions. So frequently this will be 0. So a lot of times x will just equal this. That is not always the case. Do not always take whatever it is, x naught, t naught, whatever initial condition thing. It's not necessarily starting for 0, so don't just always fill in zeros for those. Same thing with this right here. When you're going to do a simulated ball drop in the lab, when you start, the ball starts where it starts. Its initial velocity, which is this, starts at 0. So this whole piece gets wiped out here. V naught times t just becomes 0. The equation becomes very simple and easy to manage. You do not, most of the time, V naught is not going to equal 0 because that would be way too easy, right? So just pay attention to what those mean and when you use them. You can also use this as x final and x initial. So if that helps you, and then frequently this is flipped over on the other side so that it's a positive x naught plus V naught t, and it just equals x. But so that's your second equation. So here are 3 other equations that are also really useful. So basically these 5 equations are super important. This one here, equation 2-17, this isn't a real one. This one will help you out sometimes, but it's just kind of taking an average here. You just have basically v1 plus v2 divided by 2, so it's taking an average velocity. And then when you multiply it by time, that's one of the other things to keep in mind. The dimensional analysis of it, you should always keep track of the units, right? So you can see that this is a velocity, it's meters per second. This is a velocity, it's meters per second. When you multiply that against time, the seconds cancel, you're left with meters. This then equals x, which is also meters, right? So this equation is true, it works. So if you're not going to have to do it in for this class, obviously, because it's online, but if you ever need to memorize these things and you're not sure whether or not you did them correct or not, just remember, you can check the units to see if it works out. Okay. This is the table of equations, right? So these are the 5 equations right here. They're super important. I would write them down. I would keep them on a card or something near you. And when you do all these problems, you're going to have to use them over and over again. Again, I will go over this in the video, but something I will do is when I go through a problem, I will make a little table of information and say, okay, the problem gave me velocity, right? And it gave me acceleration or whatever. And once I get all those things written down, then I can see which variable I'm missing, right? So I say, okay, I'm missing time. I don't have any, they didn't give me any time information. So I can use this equation to figure out a velocity, right? But maybe I didn't have the velocity up here. So now I can plug in the velocity information in here to find out, say, time or something. Again, it's not a specific example, so it's not going to make a lot of sense, but I will go over this in the problem videos when I actually do one. And then there's some more equations down here for the checkpoint 4, and I guess I already popped the answer up, so it's whatever. Just look at it on your own there. Okay, the picture on the right is one of those things that you're kind of told. Gravity affects everything equally. And the one thing you're going to learn to do in freshman physics is to ignore pretty much everything all the time. So you're going to ignore air resistance. You're going to ignore basically anything that makes the problem difficult. And as you move on, you're going to have to incorporate this in, you know, your upper division classes, possibly graduate school if you go there. I was in the PhD program, I think, before we even thought about adding air resistance to anything. It's ridiculous. Like, it's like you finally made it when they finally add air resistance to something. But if you watch the videos on this, you can. I had a video previously incorporated in the presentation of this, but I don't have it attached, and it's become too difficult to pop in and out of this program. But you could definitely look up the videos where they're dropping like same thing in the picture, like an apple and a feather. And if you do it in a vacuum, you can see they fall and they hit the ground at the exact same time. There's like a huge vacuumed cylinder that NASA uses to drop things. It's some pretty cool videos. You can look it up. Okay. But basically, it's just saying that 9.8 meters per second squared, the acceleration of gravity, is affecting everything equally, at least on the surface of Earth. Okay, you got free fall acceleration. So again, we take out air resistance, which also means that if you take out air resistance, you take out terminal velocity. Terminal velocity is just the highest velocity anything can reach, right? So that depends on usually the shape of the object. So if you drop something like a bowling ball, it's not going to be affected as much by air resistance as if you dropped, like, you know, a trampoline or something like that. The trampoline is going to catch like a lot more air, if you can picture that, where the bowling ball is not. The air is going to slip around it and it's going to be easier for it to fall. So the terminal velocity of things can be very, very different. But we're not dealing with any of that with this because we're ignoring the air resistance. frequently, I'll tell you in the problems, be careful with how the problem is worded. In this presentation, it's 9.8. Frequently in the book, it might be written as 9.81. So whatever it says, and you're like, I don't know which one to use, because it may end up affecting the answer by the time you're done all the equations. Whatever it's doing, or whatever it's using in the problem, just use that, if that makes sense. If you're given 9.8, use 9.8. If you're given 9.81, use 9.81. Okay, so again, since we're ignoring air resistance, it's saying that we're these things don't matter anymore: mass, density, shape, etc. Here we have free fall acceleration is downward. It's going to be the minus y direction, right? So you have the constant acceleration equation. The free fall acceleration near Earth's surface is, this negative 9.8. They're saying the g is basically the magnitude. It's 9.8. So don't assume that gravity, like the acceleration in gravity, is just negative 9.8. If it's negative, it's because you're using negative g. And most of the time, that's going to be up to you. Again, that's a decision you make when you pick the coordinate system. And again, I don't think these answers are already on the slide, but yeah, so spoiler alert, I guess. There's the answer, there's the question. But basically it's saying that you can see at the bottom it says, like, basically the sign is positive, then the sign is negative. The ball's acceleration is always negative 9.8. A key point of what it's saying is that negative 9.8 means it's pulling it downward, right? Okay, here's another problem. I'll do this later. And the other one. Here we go again with the plots. I told you can't get away from the plots. Okay, so these are integrals. These little integrand symbols. Most of you, you may touch on this in Calculus 1. You're not going to get to most of the integrals until Calculus 2. So most of you may not have seen these symbols at all. You may not know what it is. The easiest way to explain it, if you don't know what it is at least the procedure. You're doing the reverse procedure of a derivative. So if you take the integral of something, you can basically undo what you did by taking the derivative of it. Now, what that means, what it actually is, that doesn't really explain anything. That's just kind of the procedure of what you can do to achieve it. But obviously, there's a whole section of math dedicated to it. I can't make it that simple. We might get into this more. I need a whiteboard or something to do more with it. So I'll just leave it at that. But basically, this thing is saying it's giving parameters in which you're performing this procedure, this mathematical procedure. So it's between the initial time and time 1. So it's between these two things. So they call this a definite integral, right? So in this case, basically, if you have, it's just labeled as variables T0 and T1. When you would do it, you would get an answer in terms of T1 and T0. A lot of times when you do these, you have numerical values. So when you have these numerical values, you're going to end up putting them in here, and then you're going to get a numerical answer for it, unless you have more variables, like this A. This A is representing a variable, and we don't know what it is, so... But again, that's touching upon a whole subject that isn't easily explained just over a microphone, I guess. So we're talking about integrating velocities. So basically, again, I don't know how much of this to get into because I don't know if you've seen it. Basically, by doing the integral of this, you're going to end up multiplying this by a t. So you're going to have vt, which, if you remember, is then meters per second, and then it's going to be multiplied by a time, so the times will cancel, seconds and seconds will cancel, and you'll be left with meters. And that's how you're going to end up with x1 and x0. Okay, more plots. This is it. All these are in the book too. If you get, these are examples, they're just in the book. I believe this has to do with like whiplash or something. Yeah, it says over there, person's head and torso in a whiplash incident. So you get the torso and the head, and then basically what they're showing you is, um, if you figure out the area under the curve, that's like doing the integral mathematically. So, for instance, what are we looking at here? So it's looking at area A. So the area underneath this portion is 0, right? So this equals 0. And basically, so it's saying to calculate the torso speed, so it's doing just the torso, we can look at the area under the curve, which that's what these integrals are attempting to do. So you have the area under the curve, you have A, so the area under that is 0. B, what they're saying is we're going from, and something, this is probably in milliseconds. Yeah, because this one's in milliseconds. So yeah, okay, so it's saying that this is between 40 milliseconds and 100 milliseconds. So this is 60 milliseconds converted to seconds, right? We just moved the decimal 3 places. So this is actually 60 milliseconds. So that's the distance between here and here for B. Now this is multiplied by 50 meters per second, which is the top acceleration it gets to. And then the initial acceleration is 0. So basically we're saying if we multiply this by half, we're just getting half the velocity, right? Because if you added up this point and then divide it by 2, it's 50 plus 0 divided by 2 gives you 25. That's all this is doing. 50 divided by half is 25. So you multiply that by the seconds, and then you get 1.5. And then area C is just constant, so you go from 100 to 110. That's 10 milliseconds. And then, so that's this portion, and then it's just constantly 50 meters per second squared, and so you get this answer. And then they just do the total. Okay, so we're at the summary. We made it to the end. I haven't been timing this at all. I feel like it's long, but hopefully, even if these go over how long they're supposed to be, again, you have the option of going back and pausing things and looking at it again. So again, if you have any questions or anything, please email me. If you need to come see me, like I said, I'll try to remember to post my lab schedule so you can come in and see me in the lab. I may actually have some of you. I'm teaching a 180 lab. I forget what time and what day. I think it's Thursdays, but I'm not sure. So you may actually also be my student in there. But like I said, if you have any questions, let me know.